Hello and welcome to Chemistry with Dr. Clark. In this video, I'd like to talk about the standard Gibbs free energy of formation, and I'd like to do some practice problems. Now, this really is the second video in kind of a series. I did do a video called Standard Gibbs free energy of formation, and it talked about the concept behind these problems. So if you're not exactly sure the background, or you'd like to know the background, you might want to pause this video and go back and take a look at this other one, Standard Gibbs free energy of formation. In this one, what I'd like to do is take the concept and apply it to some calculations. So I'd like to take it and add the practice. But let's start in the exact same place that the other one did. Okay, we started with a definition of what the standard Gibbs free energy of formation is. And the idea is that you're going to form a compound from its elements at 1 atmosphere of pressure and 25 degrees, and then you're going to measure the amount of Gibbs free energy that's associated with it. And then those values are put in a table. So here's my table of values. So now if I were to just pull something from this table, let's say that I would like to talk about, let's say, carbon dioxide. So in the table, I've got a carbon dioxide gas, and I've got a value of delta G of formation. So what this represents is me making carbon dioxide from its elements. So if I'm going to make some carbon dioxide gas, what elements do you need? Well, I need a carbon, and I need an oxygen gas. Oxygens like to come as pairs, so it's an O2. If you look up the states, whether they're solids, liquids, or gases, and your periodic table is probably color-coded for that. Usually solids have black symbols, liquids have blue symbols, and gases have red. You'd see that the carbon is normally a solid and oxygen is normally a gas. And if you attempt to balance this, you have one carbon to one carbon, and you have two oxygens turning into two oxygens. So this is already balanced. So when I talk about the formation of carbon dioxide, this is the reaction I'm talking about. I'm talking about the carbon and the oxygen coming together to form carbon dioxide. And when this reaction happens, there's a change in the Gibbs free energy, delta G. And the table gives you the value. It's a minus 394.4 kilojoules per mole. Now, you have some extra pieces on your formula. This specific reaction is a formation reaction because I am forming the carbon dioxide. That's why there's an F. This reaction is happening at 25 degrees Celsius and 1 atmosphere of pressure. That's considered standard conditions, and it's so standard that we have a symbol for that. That's the degree sign. So the little degree sign here just means you're at 25 degrees and 1 atmosphere. So you can look up the amount of Gibbs free energy that's associated with forming any compound you want, right? I have a very small table here, but you can get tables that include practically every compound you could think of. Now, I have noted the oxygen gas here. Let's say that I would like to make some oxygen gas. So I would like to make some O2 gas. Well, what element are you going to make O2 gas out of? Oxygen. Oxygen likes to come in pairs, so it is an O2. It's a diatomic molecule. And if you look up whether it's a solid, liquid, or gas, turns out it's a gas. So if you're going to take some O2 gases to make some O2 gases, have you really done anything? No, you haven't done anything. So because you haven't done anything, the Gibbs free energy for this is going to be 0 kilojoules per mole. Because you really haven't done anything. You've gone from O2 gas to O2 gas. If there is no change, there's no change in the Gibbs free energy. So it's 0. Now this is true for all elements in their standard states. So if I wanted to make, say, Cl2 gas, what element do I make Cl2 out of? Cl. They are diatomic. They like to be in pairs. And if you look up whether they're solid, liquid, or gas, they are a gas. So again, no change. Cl2 gas turns into Cl2 gas. So the delta G of formation at standard conditions would be 0 kilojoules per mole. Now, as chemists, we're a little bit lazy people, okay? I do not want to put things in this table if they're zeros, right? Like O2, 0. I could put Cl2, 0, right? I could have a bunch of things in here that are zeros, but it would take up space, it would take up time, and I don't want to do that. So, what you have to remember is if you're making an element from itself, there is no change. So what we tend to do is we leave these out. Anything that is equal to 0, we tend not to put into the table. Okay, so any element, the Gibbs free energy of formation is going to be 0 because there really is no change. So when you're doing a problem, if you find a number that doesn't have, or a compound that doesn't have a value for it, then most likely the value is 0, right? Because the only thing that we really leave out of the table that you would need is the ones that are equal to 0. And it would be just the elements. Like let's say you wanted to make iron solid. Well, what do you make iron solid out of? I make iron out of iron, solid, right? There's no change. The delta G of formation under standard conditions here would be 0 kilojoules per mole, right? Because there is no change. So if you have something missing from the table and it's just an element, then the value is 0. And we have left them out on purpose because we don't want our tables to be massive, right? We would like to condense them. So let's take a look at how we would use these in a problem. Okay. So, let's cover up the second one. The problem would say, use a standard Gibbs free energy of formation table, voila, here's our table, to determine the change in Gibbs free energy for each of the following reactions. Okay? Now, this is not a formation reaction, right? This is a double replacement or double displacement, right? The sodium and the hydrogen are going to switch places. Hydrogen comes over here. HOH forms water. The sodium comes this way to form sodium chloride. Okay, so this is not a formation reaction. But I can use the standard Gibbs free energy of formation to calculate the change for this whole thing. All right, let's break it down into 2 steps. Let's say that instead of going straight from here to here, what I'm going to do is break this down into its elements and then take those elements to reform the products. Think about it like when you were in one of the lower grades, okay, and they brought in like Lego blocks or some sort of building blocks. So you get this little tiny bucket of Lego, and then you're told to build something. So you take your little tiny bucket of Lego and you build an airplane, okay? It is the best airplane that there was ever built out of Legos. Okay, so you got this beautiful little airplane. And then you pass it to the person next to you, and it's their turn to play with it. So what do? They take the airplane apart, and they re-put it back together, and it's the world's nicest car. Right? So you use the exact same pieces. The pieces that you started with are the pieces that your friend ends up with. But you put them together to form an airplane, and they use them to form a car. Right? The same idea here. These are made out of blocks, out of pieces, right? Sodium hydroxide and HCl, they're made from pieces. So if I take them apart into their atoms, then I should be able to rearrange them and put them back together to form something new. Start with an airplane and end up with a car. So if I were to take this apart, sodium hydroxide is made up of sodiums and oxygens and hydrogens. The HCl is made up of hydrogens, well, I've already got those listed, and chlorines, right? So if I take these apart, I get sodium, oxygen, hydrogen, another hydrogen, and a chlorine. Sodium, oxygen, hydrogen, and chlorine. Now, kind of like when we were looking at our table a minute ago, you do have to talk about which ones come as diatomics, right? O2s, and which ones don't. So if I look at this, sodium likes to be by itself, so it's just sodium. Oxygen does like to come in pairs. Hydrogen likes to come in pairs. and the chlorine likes to come in pairs. So if you take all of these things apart, you get back to the original building blocks, the original pieces. And then if you take these pieces, you can put them back together to form new things, right? If I put the sodium and the chlorine together, I can get sodium chloride. If I put the hydrogen and the oxygen together, I get water, right? So you've built something out of your Legos, you take it completely apart, and then the person next to you builds something new. This is what you had built, you take it apart, and then you build something new. Well, now, isn't this a formation, right? If I ignore this part, this is a formation. I am taking the sodiums and chlorides and forming sodium chloride. I'm taking the oxygens and the hydrogens and I am forming water. So if I want to talk about the change in Gibbs free energy for doing this, I can just read them off the table, right? Because I am forming one sodium chloride. So I've got the delta G of formation for sodium chloride, because look, I'm making it. So what's the Gibbs free energy of formation for sodium chloride? If I come look at my table, it's like way down on the bottom. It's minus 384.1. So this would be a minus 384.1 kilojoules per mole. And that's for the sodium chloride. But what else am I making? I'm also making water gas. So I can also look up the delta G of formation for water gas. Now you do have to be careful, because in these tables we do try and trick you. Because I don't have water here once, I have water here twice. Where's my water? Here you go. I've got water gas and I've got water liquid. If I was being really mean, I'd have water solid, right? Water solid, water liquid, water gas. You have to make sure that you choose the right one because they have different values. So for this particular problem, we're talking about forming some water gas. So forming water gas would be this, negative 228.6. So negative 228.6 kilojoules per mole. And that's for the H2O. So if I want to talk about the total amount of Gibbs free energy change, well, I have to add them together because I'm not just making sodium chloride, but I'm also making water, right? So I'm making sodium chloride, making water. So the delta G for this is going to be those two added together. So 384.1 negative plus 228.6 negative gives me a negative 612.7 kilojoules per mole. Okay. Now, you do notice that I dropped the F for formation because eventually this is going to be for this reaction. And this is not a formation reaction anymore, right? This is a double replacement. So I am going to drop the formation. Okay, so I just ditched it here because this is a different reaction. Now, if we're talking about how does the delta G change for this whole thing, you can't just consider half of it, right? I do have to consider what's happening out here in the beginning. I have to consider taking the sodium hydroxide and HCl apart into their atoms. Well, now that's not a formation, right? I am not forming sodium hydroxide and forming HCl. I'm actually taking them apart. It's like the opposite of formation. Now, the really nice thing about opposite of formation is that it's the same number, it's just opposite sign. So let's think about melting versus freezing. If I have to put heat in to melt something, then I have to take the heat out to freeze it. So one would be a positive because the heat goes in, and the other would be a negative because the heat comes out. Right? So it's a change if you're doing it in the opposite direction. So instead of forming, I am taking it apart. I'm going to be able to use all the same values, but the sign is going to change. Because I'm not putting them together, I'm taking them apart. Okay? So let's do that. So for this one here, I have sodium hydroxide that I am taking apart. So if we're going to talk about the sodium hydroxide, let's do my delta G. And I'm going to leave off the F because I'm not forming it, I'm decomposing it, right? Breaking it up. So if I look up the value for sodium hydroxide, all my sheets are kind of gone sideways on me. All right, there we go. That's better. So I look up sodium hydroxide, it's here. So the value is 377.0 if I was going to form it. But I'm not forming it, I'm taking it apart. So instead of being a negative number, it should be a positive number. So that's going to be 377.0 kilojoules per mole. And that's for the sodium hydroxide. I changed the sign because I'm not forming it, I'm breaking it up. Now, what else am I breaking up? I'm breaking up the HCl. So if I'm breaking up the HCl is here. To form it, I would get a minus 95.3 kilojoules per mole. That's the amount of Gibbs free energy I would get. But again, I'm not forming it, I'm breaking it up. So I'm going to get the opposite. So the delta G, and again, leave off your F, instead of being a negative 95.3, it's going to be a positive 95.3 kilojoules per mole. Now, like the last time, right, I am going to decompose the sodium hydroxide. I'm going to decompose the HCl. And because I'm doing both, I really need to add it up. So my delta G is going to be 377.0 plus 95.3. So the total change into Gibbs free energy for taking apart my reactants is going to be 472.3 kilojoules per mole. Now, this is the total amount of energy to take the reactants apart. This is the total amount of Gibbs free energy to put them back together. And in this process, you're doing both, right? You are taking them apart and you're putting them back together. So in the end, you need to add both of them up. So the Gibbs free energy for this whole thing is going to be the amount that's associated with the products and the amount that's associated with the reactants. So it's going to be the minus 612.7 kilojoules per mole. And it's going to be the 472.3 kilojoules per mole for the reactants. And if you put those two together, your Gibbs free energy change will be 612.7 negative plus your 472.3 gives you a minus 140.4 kilojoules per mole. And that's the change in the Gibbs free energy for this chemical reaction. Notice we don't have the F here because this is not a formation. Now, that's the big idea for this whole process. But I'd like to streamline it because usually if you're given an assignment or a set of problems to do, you don't have just one of these, you have a pile of them. So we would like to make this a little bit more streamlined, a little bit more faster. So let's change up a little bit how I'm going to do this. Let's rewrite my equation. So I had sodium hydroxide solid plus HCl gas turning into sodium chloride solid and H2O gas. Now, I did have to look up the delta G of formation for all of them. Some of them I changed the sign, some of them I didn't. Let's say that I'm busy. I don't want to have to remember which ones do you change the sign and which ones do you not. So what I'm going to do is I'm going to write right underneath each of these the value that comes straight off the table and not worry about changing it. So there's not going to be any changing of the values. Okay, so let's move this up. So if I look up sodium hydroxide was here, and the value is minus 377.0 kilojoules per mole. Now, I know that this is supposed to change sign, but I don't want to have to think about that. So right now, I'm just going to write the values down and not change them at all. No changes. So HCl, when I looked it up, was a minus 95.3. Minus 95.3 kilojoules per mole. When I looked up the sodium chloride was way down here on the bottom, remember? Negative 384.1. So negative 384.1 kilojoules per mole. And when I looked up the water, I had to be really careful because this is gas water. So I need to choose gas water. Negative 228.6. Negative 228.6 kilojoules per mole. Okay, so I've just written them straight off the table without any modifications or changes, no sign changes. Now, if you look back to what I did before, I did add up all of the products and I did add up all of the reactants. So let's do that again. Let me just divide it into reactants versus products. So I'm going to add up all the reactant values and I'm going to add up all of the product values. So here on the reactant side, I had 377 negative plus a 95.3 negative gives me a negative 472.3 kilojoules per mole. If I add them all up here on the product side, so that's 384.1 negative plus a 228.6 negative gives me a negative 612.7 kilojoules. Okay, so far I just looked up the numbers, added them up for the products, added them up for the reactants. Now, I don't want to have to remember which one is supposed to change sign. Like if you look back, the reactants, we said we were actually breaking them up instead of forming them. So we changed the signs, right? This should be the opposite sign. Now, the way that I'm going to get around having to remember it, I'm going to call this a little formula. I'm going to say if you want the delta G for the reaction, you're going to take the number for the products and you're going to subtract off the number for the reactants. Products minus reactants. Because if I subtract off the reactants, what happens to a negative negative? Negative negative turns positive, and that's exactly what I had. By writing the formula like this with the negative sign in front of the reactants, the negative sign in front of the reactants will automatically change the sign here. So you don't have to worry about remembering to change the sign. It's built into the equation. So if I do that, delta G is my product. So that's a minus, whoops, that was kilojoules per mole, missed that. So minus 612.7 kilojoules per mole minus the minus 472.3 kilojoules per mole. Negative and negative is positive. And if I put that in my calculator, okay, negative 612.7 is already there, plus a positive 472.3 gives me an answer of minus 140.4 kilojoules per mole, which I believe is the exact answer we got the last time. Right? Here, we thought of it more actually as it happens, right? Talked about it as taking them apart and then putting them back together. This is based on that, but there's less worrying about what's actually happening, and it's more of a step 1, step 2, step 3. Right? Step 1, write down the values as you see them from the table. Step 2, add up the products, add up the reactants. Step 3, put them in this little formula. The change in Gibbs Free Energy is the products minus the reactants, and that'll get you where you want to be. Okay? Now, this works for delta H and delta S. Changes in the enthalpy, changes in the entropy. I do have videos that talk specifically about those things. So if you're doing a problem that involves enthalpy changes of formation, heats of formation, there's a video. You can go and watch it, and it'll do problems specifically for that. If you're talking about entropy changes of formation, well, I have a video that specifically talks about that. The process is exactly the same. It's just instead of looking up values of delta G, you're going to look up values of delta H or values of delta S. Okay? So if you are looking for the alternatives, I do have videos for those. Please take a look at them. Okay, so let's use this more streamlined approach for the second problem. So the way that I'm going to do it is I'm just going to look up the value for each of these chemicals from my table, write them underneath, add the products, add the reactants, and then do reactants minus products. Products minus reactants. Got to make sure that I don't mess it up, right? It is products minus reactants. For a minute there, I doubted myself, right? This here little formula, if you're going to use it, you better make sure you memorize it because you don't want to do it backwards or it's going to mess with your sign. All right, so let's say that we do this one, and I'm going to need to stretch mine out a bit because, well, my pen takes up a lot of space. So let's say I rewrite it. 3Fe2O3 solids plus a CO gas turning into 2Fe3O4 solids and a CO2 gas. There. That gives me enough space to find my values and write them down. All right, so let's move that up. Let's add some extra space here to do some calculations at the bottom. And let's pull back our friendly table. So step number 1, I'm going to look up the value for each of the chemicals from the table. So my first chemical is an Fe2O3 solid. So if I look here, I do have an Fe2O3 solid. The value is a minus 741.0 kilojoules per mole. So this is going to be a minus 741.0 kilojoules per mole. Now, I do have an issue with this problem that I didn't have before. With the first problem, I had 1 sodium hydroxide, 1 HCl, 1 sodium chloride, and 1 water. I had 1 of each. But this problem here, in order to balance it, I have 3 of these, 1 of these, 2 of those, and 1 of those. The values of heat in this table, the values of enthalpy change, they're per mole. They are for 1. So when I looked up the value of minus 741, that's for 1 of these, not for 3. It's for 1. So if I want to know the amount of Gibbs Free Energy change for 3 of them, then I need to multiply this by 3. Okay? The values here are for 1. This is for 1 carbon dioxide. This is for 1 Fe2O3. This is for 1 water gas, right? Remember how when we did the examples at the very beginning, we were very careful to have 1 of the products. The product was always going to have 1 of them. All right, so if you're going to have 3, you got to multiply by 3. Now, this 3 out in front actually represents moles. So this is 3 moles times negative 741.0 kilojoules per mole. Now, the really nice thing is if you've got moles and you've got per moles, they cancel, right? This is just regular old moles. This is moles in the denominator. Moles and per mole cancel. So if I multiply these out, that's going to be 3 times 741.0 negative. That gives me a minus 2,223. Moles and moles are gone, so it's just kilojoules. Right? 741 is the Gibbs Free Energy for 1 of these. But because you have 3, you're going to multiply by 3. The moles will cancel and it'll just leave kilojoules. All right, let's talk about the carbon monoxide. So if I go to my table and I look up carbon monoxide is right here. It's 137.2 kilojoules per mole. So that would be minus 137.2 kilojoules per mole. Now, this is the amount of energy required to make 1 of them. How many do you have? I have 1 of them. Now, the thing that I kind of skipped over in the top equation is that multiplying by the number that you have, we really should do that even if there's only 1. So even though I only have 1 of the carbon monoxides, that's like 1 mole of them. So again, you have moles, you have per mole, and they cancel. So that gives you 1 times 137 kilojoules, which is 137 kilojoules. So minus 137.2 kilojoules, right? In the first one, because I wanted to explain the overall process, I kind of left that out, right? I said this number goes with 1, 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 and I just left the per moles all the way to the bottom. In reality, though, when you do these problems, you really should multiply by the number of moles in front by the amount of Gibbs free energy that goes with the chemical. Number of moles in front times the Gibbs free energy that goes with it. Okay? Now, we know that once you find the numbers for the reactant, you're supposed to add them up. So I'm going to put these two together. So I've got a minus 2,223 already in my calculator. And I'm going to add the 137.2 negative. So the total amount of Gibbs free energy for the reactants will be a minus 2,360.2 kilojoules. Okay, and that's my reactants done. Let's move on and do the products. Okay, so let's move this, and let's move these over a little bit. Okay, so I'm going to look up the Gibbs free energy for both of these two chemicals. So if I look up Fe3O4, Fe3O4 is right here. Wow, that's a big one. So that's going to be a minus 1,015.5 kilojoules per mole. If I look up the value for carbon dioxide gas is, right here at the top. Carbon dioxide gas. So that's going to be a minus 394.4 kilojoules per mole. Now for both of these, this is the number to make just one of them. If you're making more than one, you're going to have to multiply, right? I don't have one Fe3O4, I have two of them. So this is going to multiply by 2 moles. This is the number for one, and technically that's the right number. But if you're going to be canceling out moles everywhere else, then you should probably multiply this by the moles as well. So this is 1 mole as well. Right? So you got 2 of these, so you multiply it by 2. You got 1 of these, so you'll multiply it by 1. So we'll work out this one, we'll work out this one, and then we'll add them together. All right, so pull out our calculator. That is 2 times 1,015.5 negative. That gives me a minus 2,031. Now remember, moles and per moles cancel. That just leaves me with kilojoules. So that's kilojoules. If I do the other one, 1 times a negative 394 is a negative 394.4. And again, moles and per moles cancels, leaves me with kilojoules. And this is the products. This is the amount of Gibbs free energy that goes with this product. This is the amount of Gibbs free energy that goes with this product. And I need a total. So I'm going to add those two together. So this one plus this one. So I've already got to negative 2,031 in my calculator. And I'm going to add on the 394.4 negative. That gives me a total of minus 2,425.4 kilojoules. The total Gibbs free energy that goes with the reactants, the total Gibbs free energy that goes with the products. Now, we know that this is supposed to keep its sign because I'm actually forming these. We know that this sign should change because I'm not forming these, I'm taking them apart. It's the opposite. And the easiest way to do the formula is delta G equals products minus reactants. Because I want the product to stay as it is, but I want the reactant to change sign. And so if I put a negative in front of it, that changes its sign. So the delta G for this would be the product minus 2,425.4 kilojoules minus the reactant, which is a minus 2,360.2 kilojoules. And again, if we haul out our trusty calculator, 2,425.4 negative minus a minus becomes plus 2,360.2 gives me a final delta G value of minus 65.2 kilojoules. Now you'll notice that I dropped the F because it's no longer a formation, but I did keep the degree sign because this is still happening at 25 degrees Celsius and 1 atmosphere of pressure. This is the change in the Gibbs free energy for the original equation. If you took these two reactants, put them together, and made these two products, and you measured the change in the Gibbs free energy, this would be what you'd get. All right. Let's say that we try just one more. Alrighty, so let's say that, whoops, it'd be nicer if we had a clean sheet of paper. There we go. Let's say that we'd like to do this one. You've got 2 H2S gases, 3 O2 gases turning into 2 water liquids and 2 sulfur dioxides. So remember the steps. Look up the numbers, multiply them by whatever is out in front, total the reactants, total the products, and then subtract them. Okay, like before, I do need some extra room, so I'm going to rewrite it. H2S gas, 3 O2 gas, turning into 2 H2O liquid. Be careful, this one's liquid. And 2 SO2 gas. Okay, I'm going to draw a line here to separate my reactants from my products because I'm going to add and add. And then I'm going to pull out my sheet and look up my values. So if I look up H2S gas is right here. So it has a value of minus 33.6 kilojoules per mole. Now, if I look up my O2 gas, in this table it actually is here, right? You can see it's a 0. But normally, O2 is an element. It has a Gibbs free energy of 0. So normally, this one will be left out of the table. So when you're working your way through your equation, if you find something that's missing, what you have to train yourself to do is to think, oh, is that an element? Because if it's an element, it has 0 Gibbs free energy of formation. Okay? So for the oxygen, it is a 0 because it is an element. 0 kilojoules per mole. If you're going to make an element from itself, you're not really changing anything. That's why it's a 0, right? We talked about it at the beginning. Now, I do need to multiply by how many? You have 2 of these, so that is like saying that you have 2 moles of them. And you have 3 of these, so that's like saying you have 3 moles of those. And remember, at the end, you are going to add them, right? So this plus this gives you these numbers plus these numbers. Now, if you go canceling, moles and per moles cancel. Moles and per moles cancel. So it's just going to leave you with kilojoules and kilojoules. So if we put this in our calculator and we do the whole thing all at once, 2 times 33.6 negative plus 3 times 0 gives me a total of minus 67.2 kilojoules. Right? This is the number for making one of them, but you have 2, so you have to multiply them. This is the number for making one, but you multiplied it by 3 because you got 3 of them. And then in order to get the total for the reactant, you had to add them up. So number for the first reactant, number for the second reactant, and you just add it. Okay, let's move over to the product side. So on the product side, you're going to make H2O liquids. Now be careful, there's more than one water on this table. H2O liquid is here. So to make one water molecule liquid, the change in the Gibbs free energy of formation is 237.1 kilojoules per mole. If you look up the value for SO2, SO2 is here. The change in the Gibbs free energy for forming an SO2 is minus 300.2. So minus 300.2 kilojoules per mole. This is the value for one. This is the value for one, but you've got more than one, right? You've got 2 moles of the water. You've got 2 moles of the sulfur dioxide, and you're going to have to add them together. right? Because eventually you're going to want the total for the products. So 2 times the value for the water plus 2 times the value for the sulfur dioxide. If you put them in your calculator, and again, you can do it all in one shot, 2 times 237.1 negative plus 2 times 300.2 negative. So over here I get a total of minus 1074.6. Just like the last couple of times, moles and per moles cancel, leaves you with kilojoules. Moles and per moles cancels, leaves you with kilojoules. So this would be in kilojoules. And then to finish the whole thing off, delta G for the reaction is going to be products minus reactants, because I want this one to stay the same, but I want this one to change signs. So the delta G is my product minus 1074.6 kilojoules minus a minus 67.2 kilojoules. So the change in the Gibbs free energy would be, okay, I've already got the minus 1074.6 in my calculator. Minus a minus is plus, so it would be plus 67.2 gives me a minus 1007.4 kilojoules. So for this reaction here, if you measured the change in the Gibbs free energy, the change would be a negative 1007.4 kilojoules. Okay? For these here, that's the power of them. Because we have tables with delta G's of formation for practically everything, right? You can look up a value of delta G of formation for practically anything you want. And because you can look them up for anything you want, that means you can do this calculation for any reaction that you're given, right? I can give you any reactants, any products. You look up the values, add the reactants, add the products, and then do delta G equals products minus reactants, right? This is very powerful. And like I said a little earlier in the video, you can do the exact same calculations for delta H's, and you can do the exact same calculations for delta S. I do have videos explaining both if you want to take a look at them. So as always, thank you for joining me here at Chemistry with Dr. Clark.